I may have to take some time to switch it and things like that.
It is good. We are fortunate that such a thing didn't happen.
Yeah.
Professor Subramanian, how are you?
Fine, fine.
Very good, very good.
Yeah.
Dr. Saratno, should we begin? I have a 20-second
1
start.
minute, I think. Now it is, my watch is showing 9:49.
Okay, 1 minute.
1 minute.
Good, good, good.
Yeah, now it is 9:50.
Okay, should I give the...
Yeah. Please.
Okay. My name is Professor Jesse Deutsch. I'm a professor at SRM University AP in the mathematics department. Honorable guests and esteemed colleagues, I would like to open the first conference organized by the mathematics department of SRM University AP, namely our mini conference on number theory and related topics. We would like to thank university management for their support and encouragement. Also, I would like to thank those younger members of the mathematics department who made major contributions to developing this initiative. At this point, I would like to introduce Department Head, Professor V. Cannon, who has the honor of giving us the opening remarks. Professor Cannon, please.
Thank you, Professor Jesse Josh. I'm happy to see that this kind of activity is starting now. I welcome all the participants and I welcome all the invited speakers. And in the opening remarks, I'm thinking of saying a few words about this activity and our university and our department. SRM University AP is one of the young universities in the country. It was started only in the year 2017. Actually, we all faculty members in the Department of Mathematics here joined only after 2018. Therefore, I can say that our department is only 3 years old now. The university has very ambitious plans. The department, while starting, it started as a service department, taking courses for the BTech programs. But now, following the new education policy of our government, this year, we are planning to start a 4-year program in BSc by research in mathematics. In that 4-year program, we are yet to announce, and we hope that in the first batch, we will take about 10 students to start with. We will start modestly, and we seek the best wishes of all of you for the success of all our activities. At present, in the department, we have about 20 faculty members and about 12 research scholars who have registered for their PhD. We have 2 or 3 research projects, and our interests cover a broad spectrum of mathematics, including algebra, analysis, number theory, differential equations, mathematical modeling, and many others. The present event is, in a sense, the first of its kind in our department. But we are planning many other events, not exactly similar to that, but something like that. For example, we are starting a series of distinguished lectures in the form of webinars, one lecture per month from a distinguished mathematician in the world. We are starting that program. At present, the present program is a mini conference in number theory. We have 4 or 5 youngsters to assist Professor Jesse Josh, our young faculty members who are specializing in number theory research. The university is having a very broad vision. And as I said earlier, it is very ambitious. And in conformity with that, our department also intends not to confine its activities within the department. Therefore, it is arranging some events that will be useful for the whole community of mathematicians. And this event is the first of its kind. I once again welcome all the participants and also all the distinguished speakers for joining us in this event. I hope with the goodwill of all of you, this program will really be successful. It will be a 3-day program of a series of lectures from eminent number theorists in the nation, in the country, and the world. Thank you. The program opening remarks have been made now after a prayer that I did mentally. Thank you.
Okay, thank you, Professor Cannon, for your wonderful remarks. Should we take a minute or two break, or should we start Professor Balasubramanian?
Yes, I think more participants are slowly joining. Let us have a break of 2 to 3 minutes.
Yeah, so that I can probably have my slide shared.
Yes.
Yeah, sure.
Good. You can make me a co-host and you can.
Yeah. I think you can share.
Okay, fine. Is this clear?
Yeah, this is visible to
Perfect.
me at least.
Yeah.
It is visible.
It's 10 o'clock according to my computer. Should we start?
Yes.
Okay, sure.
Okay. So let me introduce Professor Balasubramanian. For our first talk, we have the honor of listening to Professor Ramachandran Balasubramanian, who will be speaking on the product of three primes. He is known to all of us for solving a case of Waring's problem, in addition to being awarded with the Shanti Swarup Bhatnagar Prize, the Ordre National du Mérite of France, and the Padma Shri Award. Without further delay, here is Professor Balasubramanian. Professor, please.
Okay, thank you. Thank you for inviting me to give this lecture, as well as for this nice introduction. Yeah, let me thank the organizers for this opportunity to talk on this problem, which is still we are doing. And Professor Kannan introduced that there are number theory going on in SRM, and I am very happy to know that. But the number theory has now many branches: analytic number theory, algebraic number theory, transcendental, combinatorics, and so on and so forth. And I don't know how many of you are doing in analytic number theory, which I am going to talk on analytic number theory. This is essentially studying about the prime numbers. And this being an ongoing thing, I have given this lecture probably earlier ones, but with a bit more technical. But since more students are involved here, I have just rewritten it in somewhat a simpler form. And okay, therefore let me start. Okay, the starting point is a theorem of Dirichlet, which says that if two numbers A and Q are co-prime to each other, then there are infinitely many primes in the arithmetic progression A modulo Q. Obviously, if A and Q are not co-prime, you cannot expect more than one prime. If at all, there will be only one prime. And therefore, you would expect that the primes are distributed only in these residue classes A modulo Q, where A and Q are co-prime. And in fact, probably most of you would have seen a very simple proof in the case 1 mod 4, minus 1 mod 4, and so on. And such a simple proofs can be given only in special cases. Particularly if A square is congruent to 1 modulo Q, you can try to do something. But the cases where A square is not congruent to 1 mod Q, then there's really no way of giving any simple proof. It is always an analytic proof, which means that you study something called the L functions and study the analytic properties of the L functions and then prove that. Good. Now you say that there are infinitely many primes, and then you would like to know how many primes would be there and what would be your guess. See, the number of primes up to n, that's called the prime number theorem, which was proved for Riemann and Delaval-Poisson and others. that the number of primes up to n is around n over log n. And if the number of primes up to n is around n over log n, and these primes all distributed in the phi q residue classes modulo q, because there are only phi q residue classes A modulo q, where A is invertible modulo q, then most likely there is no reason why a prime should prefer one residue class modulo q compared to other residue class modulo q. Therefore, the normal expectation would be that the number of primes in each of the residue classes would be sort of equally distributed. And if it were so, then what you would expect is that the number of primes up to n, which are congruent to A modulo q, should be n over phi q log n. Hello? Yeah. This is a normal expectation. But on the other hand, we are not in a position to prove this result. This result is sort of very difficult, and essentially because there is something called exceptional zeros for the L functions, which gives you all the trouble. But however, we can prove it if q is bounded by a power of log n. Therefore, if you take a n and q, and if n is very large, which means that log n is bigger than a power of q, then you can prove this result. But however, this asymptotic formula can be proved only if q is bounded by power of log n. However, a weaker result can be proved for practically all the q. And that weaker result is what is called Brute-Titmarsh theorem, which says that the number of primes up to n, which are congruent to A modulo q, therefore the number of primes in the residue class A modulo q is at most 2 times n divided by phi q to logarithm of n over q. Now this result is weaker compared to what you would expect, namely n over phi q log n, which is what you would expect. But this result is weaker in two senses. Number one, the denominator is not log n anymore. It is log n over q. And also you get a factor 2. Okay, therefore, subject to these two weaknesses, that a factor 2 is you are getting, and then you get a log n going to log n over q. And then you get a bound which is essentially the same order as what you would expect. Because if q is rather small, as we have been assuming, even though this result is true for every q, but if q is rather small, then log n by q and log n will be of the same order, and therefore you are okay. Good. But now, our main interest, okay, there are other results like Bombini-Vinogradov theorem, which essentially says that the asymptotic formula holds within where you don't get an L infinity norm of the error term, but you can get an L2 norm for the error term and so on, L1 norm for the error term and so on and so forth. But the theorem that we are interested, which we want to talk about, is a theorem of Link, which says that there exists a constant C positive such that the set of primes P, which are less than q power C, covers all reduced residue classes modulo q. Therefore, if I am interested in knowing, okay, equivalently, if I am interested in knowing what is the least prime in a given residue class A modulo q, the least prime in a given residue class A modulo q, then you have to go only up to q power C. If you go up to q power C, then you will get a prime less than or equal to q, which is a prime less than or equal to q power C, which lies in the congruence class A modulo q for every A. Therefore, what is the amount you have to go? You have to go up to a length of q power C, then you would be able to see a prime congruent to A modulo q. And clearly, you see, when I said that the asymptotic formula holds only when the q is less than a power of log n, you cannot deduce from that this result. Therefore, this result again needs other tools. The other tools are again studying the L functions more carefully. Good. Now the question is that, of course, you have now got an existential result. You have got an existential result that there is a constant C such that you have to go only up to q power C. But what is that constant? Can we have something about that? it is expected that the Ylands theorem is true for any constant C bigger than 2. Therefore, you may have to go only up to, let's say, 2.01. If you go up to q power 2.01, then you should be able to see all the primes in every residue class. You take a residue class 3 modulo 7, you should be able to see a prime there. Another residue class 5 modulo 7, then you should be able to see that. Therefore, the amount which you expect to go up to C is bigger than 2. But the Ylands theorem or Ylands proof does not give the constant C somewhere around 2. It gives somewhat a bigger constant. And in fact, Pan calculated the value and got C to be something like a 10,000. That's exactly what happens. And then, of course, then you try to do whether the 10,000 can be improved, whether you can get up to 2, and so on and so forth. And the various improvements are known because we essentially doing a numerical estimations of the L functions. The value of C has been reduced to a large extent. And the best known value is essentially C is equal to 5. Euler is in 2018. And this also is valid only if Q is sufficiently large. This is something which you will always get in number theory, because then you will be getting a main term and an error term for whatever you want. And then you would expect that the main term should dominate the error term, which would happen only if the parameters are very large. And then one tries to really see how to improve the parameters. And the method of proof is by analytic methods, which means that you have to do the numerical estimations on the function LSK, which I have not even defined, but it's okay. But now let's look at another conjecture in this connection. Let P2 be the product of 2 primes. Therefore, take product of 2 primes, and then I would like to know whether if I go to a small length, it would cover all reduced residue classes. Now you see I have too many numbers. Earlier I had only P1, which is a prime, and the number of primes is around n over log n. But on the other hand, if you look at 2 primes, then you have much more numbers. And since you have much more numbers, then the conjecture of L dash Hotlisco and Sarkozy was that if you take the set P1, P2, where P1 goes up to q power 1 plus epsilon and P2 goes up to q power 1 plus epsilon, and that is precisely what you would expect, because for one single prime, you expect that up to 2 plus epsilon, you should get it. Then since you have 2 primes, then probably 1 plus epsilon, you should get it. And that should cover all A modulo Q, where A and Q are co-prime. And nothing much is known regarding that, essentially because, again, it's not very clear how one can use any non-analytic methods. And therefore, whatever you will be getting is precisely what you will be getting using analytic methods and nothing more than that. And now let's weaken the problem a little more to see whether, besides the analytic methods in number theory, which means besides studying the estimations of the LSK, some other tricks, some other ideas can be made into play. And that is P3, that is now with this product of 3 primes, and that is the title of the talk. Therefore, I take P3, which is a product of 3 primes, P1, P2, and P3. If I now take the product of 3 primes, and this was initiated by Riemann and Walker, they have observed that analogous problem for P3 can be handled by combinatorial methods. Therefore, besides analytic methods, now you can use also the combinatorial methods. And probably the first thing is to explain what is the combinatorial method that we are talking about. Yeah, this subject, which is called an additive combinatorics, has recently grown into a very vast subject in the last 30 years, and many beautiful results have been proved in these combinatorial methods. Therefore, and again, this is also a big subject and having too many problems. And we are interested only in one single problem, and that's what I want to say. Suppose A and B are finite subset of integers. Therefore, I take 2 finite subset of integers, and then I take A plus B. What is A plus B? I take an element of A and an element of B and add them. That's all. Therefore, I take an element of A and an element of B and add them, and that is what is called A plus B. And clearly, when you see, then there will be a multiplicity. For example, if A is from 1 to 10 and B is also the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then when you take the A plus B, it will have 2 and 3, 4, but 3, 4, 5, etc. will come many times, because there will be many values of A and many values of B. When you add A plus B, you will get 5. And you don't count them with the multiplicity. If you count them with the multiplicity, then the cardinality of A plus B will be precisely the cardinality of A into cardinality of B. That is very clear. That if you have two sets A and B, and then when you add A and B, and that is take an element of A and an element of B and add, and then you count them with the multiplicity, then the total cardinality will be cardinality of A to cardinality of B. But suppose you count without multiplicity. Even if you count without multiplicity, then the theorem says essentially that this number A plus B is at least as big as the cardinality of A plus the cardinality of B minus 1. Therefore, you can't find out two sets where the A plus B has too many multiplicities so that the sum goes down very much. If in the above equality holds, then you can actually check that A and B are in an arithmetic progression with the same common difference. That's the only case where the equality will hold. And if that is not the case, then you can even improve the equality. And there are many theorems there due to Riemann and others and regarding that. But what we are interested in this lecture is not the finite subset of an integer, finite subset of integers, but a finite subset of an abelian group. Therefore, let G be a finite abelian group written additively. This is very important. I mean, therefore, normally the abelian groups are written additively. And let A and B be a subset of G. Let P be a prime. And then what can we say about the cardinality of A plus B? Which means essentially I am doing the same thing. Since G is a group, there is an addition. And therefore, I can take an element of A and an element of B and add the two elements A and B. And then I get the set A plus B. And I can look at the cardinality and whether I can say something nice about the cardinality. Whether I can say some good lower bound. Let us take the simplest case. The simplest case is that this finite abelian group which I am taking is Z over PZ. And then if we take the group Z over PZ, then the theorem says that either A plus B is equal to G, or the cardinality of A plus B is bigger than the cardinality of A plus the cardinality of B minus 1, which is exactly what we had earlier. Okay. And on the other hand, the full A to be itself G and B also to be G, then A plus B will be only G. And therefore, there is no way A plus B can be bigger than cardinality of A plus cardinality of B minus 1. And therefore, that has to be excluded. Therefore, either A plus B is a full group or A plus B is bigger than cardinality of A plus cardinality of B minus 1. Now you may be wondering why I took the special case G equal to Z over PZ. Can we not do something like that for any group G? And in fact, that's not possible. Such a result cannot be extended to a general finite abelian group. Okay, let me give an example. Let H be a proper subgroup of G, and then I take A to be H, B to be H. And when you take A and B to be H, then A plus B is also H because H is a proper subgroup. And therefore, A plus B is, therefore, in the theorem of Cauchy-Davenport, A plus B cannot be G, it is only H. And the cardinality of A plus B cannot be bigger than the cardinality of A plus cardinality of B minus 1 because A plus B is also H, A is also H, B is also H. And therefore, you are claiming H is bigger than H plus H minus 1, which is not possible when H is a proper subgroup. Therefore, this theorem cannot be extended for a general group if the group has a proper subgroup. And that's exactly the reason why we restricted ourselves to G equal to Z over PZ when you don't have a proper. But on the other hand, there are many applications where you need a theorem of that type when G is a finite abelian group. Therefore, you take a finite abelian group and I have a set A and a set B, and then I look at the A plus B and I want a lower bound in the general case. And that's the theorem of Nasser. Let G be a finite abelian group. And for such an abelian group, you define the stabilizer. Stabilizer is those elements of G such as G plus X equal to X. And that's a subgroup. And now take A and B to be subset of G. and let H be a stabilizer of A plus B. And now assume that A meets lambda cosets of H. When I say A meets lambda cosets of H, I mean A has a non-empty intersection with the lambda cosets of H. Therefore, I take this H to be a subgroup, which is a stabilizer of A plus B, and therefore there will be cosets, and I will see how many cosets A meets non-empty intersection, and that number lambda, until it B meet mu cosets of H, then the same thing is true. A plus B is equal to G, or cardinality of A plus B is bigger than or equal to lambda plus mu minus 1 times cardinality of H. This also you can see whatever we saw in the integers case or whatever we saw in the Cauchy-Davenport case, I mean the same similar results. Okay, therefore if A B meets mu cosets, then A plus B is equal to G, or cardinality of A plus B is bigger than lambda plus mu minus 1 into cardinality of H. And this theorem is one of the very important theorems, cornerstones of this theory. And this theorem is what we plan to prove again, use again and again. Now, in every case, I was saying that A plus B equal to G. What are the cases for which A plus B, you can actually prove A plus B equal to G? Therefore, let's make an observation. Suppose A and B are subsets of G, and suppose the cardinality of A plus cardinality of B is bigger than cardinality of G. If cardinality of A plus cardinality of B is bigger than cardinality of G, then A plus B equal to G. Let me give a proof of that first. Okay, what is that I have to prove? I have to prove that every element G can be written as an element of A plus an element of B. That's all what I have to prove. Therefore, let us fix a G in G. And I have to prove that this G belongs to A plus B, which means that this G can be written as an element of A plus an element of B. How do I prove that? Let S be a set which is just A, and T be the dilational set B, which is G minus B, B in B. Therefore, cardinality of S, which is the same as cardinality of A, and the cardinality of T, which is the same as cardinality of B, that summation is bigger than mod G. And if you have two subsets whose cardinality is bigger than cardinality of G, then these two subsets cannot be non-intersecting. They have to have a common intersection. If they don't have a common intersection, then if you have the S and the T and the cardinality is bigger than G, then it's not possible. They will have an intersection. Okay, and therefore let's check X to be an element in the intersection. Therefore, X is S intersection T. Then this X is in S, and therefore X can be written as A, and X is in T, and therefore it can be written as G minus B, and consequently A plus B equal to G. And that's exactly what I have to do. Therefore, this is one case where you will always get A plus B equal to G if the cardinalities are big. Now let's prove the corollary. Suppose A is contained in G, and let's assume that G has a cardinality N. And if G has a cardinality N and A is bigger than N by 2, let's say 0.51 N, then obviously A plus 1 equal to G. And what I am actually interested in my final thing, since I am looking 3 primes, I don't even need the fact that A plus A equal to G, but I can need A plus A plus A equal to G. That's all what I need. I need only a weaker result. Since I need only a weaker result, not A plus A equal to G, but if A adding 3 times equal to G, then probably I do not need a condition as strong as cardinality of A is bigger than N by 2. And probably what you would think is probably something like an N by 3 should do, because if I want to add 2 of them and you want to get G, then you need a cardinality of A to be bigger than N by 2. But therefore, if you want 3 of them and add and you want to get G, then the cardinality should be N by 3 is what you would expect. But for example, therefore, can we, for example, prove that if the cardinality of A is bigger than 0.41 N, which is much bigger than N by 3, then is it true that A plus A plus A equal to G? Unfortunately, that is not true. Therefore, even though the cardinality of A is rather big, 0.41 N, and you are adding it 3 times, but even then the A plus A will not give G. Okay, let's see a counter example. And in fact, it's false, because suppose H is a subgroup of index 2. If H is a subgroup of index 2, which means that the cardinality of H is exactly is equal to half times cardinality of G, and therefore I can choose a in that H itself. Okay, for example, H itself is a cardinality bigger than 0.41 n, but therefore I can take A equal to H, because H is a subgroup of index 2, cardinality of H is n by 2, and therefore I can take my A to be cardinality of H, because I only need cardinality of A to be bigger than 0.41 n. And then you add H and H and H. But H is a subgroup. Therefore, when you add H plus H plus H, you will still H only, and your H will be bigger than 0.41, and that's no way you can do that. And of course, you can play the same trick with not only H, but also H complement. And when you take the H complement, you can actually check that H complement plus H complement is H, and therefore H complement plus H complement plus H complement will be H complement. It won't be the full of G. And H complement also will have essentially half the elements. Therefore, it will also be bigger than 0.5. Which means that in some sense I can't improve it. I mean, this 0.5 is what I need. But on the other hand, when I do the calculation, I don't get a lower bound 0.5. I get only a lower bound 0.4. And if I get a lower bound 0.4 and I want to use it, then is there some way I can improve this result? And in fact, we shall prove that this is a only counterexample. Therefore, if this counterexample doesn't exist, then the answer is true. Therefore, let's do that. Let A be a cardinality of A be contained in G, and let cardinality of G be equal to n. And let's assume that cardinality of A is bigger than 0.405 n. Just strictly bigger than 0.4 will be sufficient for us. And now we have made the following assumption, that for any subgroup H of index 2, A meets both cosets of H. Therefore, just taking A equal to H or A to be a subset of H will not work. Or A to be a subset of H complement will not work. I am assuming that for any subgroup H of index 2, A meets both cosets of H. And then A plus A plus A equal to G. Therefore, that counterexample which we saw, that the subgroups of index 2 will kill you, okay, because if A is completely contained in H or A is completely contained in H complement, still can be bigger than 0.4 n, and still A plus A plus A equal to G will not work. But on the other hand, just you assume that that doesn't happen, then A plus A plus A equal to G. And this proof is not difficult, and therefore let me give a proof. It is actually sufficient to prove that the cardinality of A plus A is bigger than 0.595 n. That is essentially because then the cardinality of A plus cardinality of A plus A, cardinality of A is assumed to be 405, and the cardinality of A plus A, suppose I can prove 595, then the cardinality of A plus cardinality of A plus A will be strictly bigger than cardinality of G, and we can use observation to say that when you add this A with A plus A, you will get the full G. That's what the observation says, that if you have two sets A and B, such as the cardinality of A plus cardinality of B is bigger than cardinality of G, then A plus B will already. And how are you going to get the cardinality of A plus A to be bigger than 0.595 n? The standard idea is, of course, the Nasser's theorem, because essentially Nasser's theorem tells you that how to get the lower bound for cardinality, given the cardinality of A, how to get a lower bound for cardinality of A plus A. Therefore, let's just use the Nasser's theorem. Therefore, let H be the stabilizer of A plus A, because that's what the Nasser's theorem says, that you take the stabilizer and see how many cosets of H A meets and how many cosets of H B meets, call them lambda and mu, and then you take lambda plus mu minus 1 times H. And let H be have an index L, which means H is of index L in G, which means that the cardinality of H will be N over L. Okay. Since A is bigger than 0.405 n, and you see now every coset will have only N over L elements. Because the group, subgroup H has N over L elements. If the subgroup H has N over L elements, every coset will have N over L elements. And therefore, but A has too many elements. And if A has too many elements, it has to meet many cosets. Okay? Because a few cosets will have only few elements. So every coset will have only N over L elements. And since A has bigger than 0.405 n, A meets at least lambda cosets where lambda is bigger than cardinality of A by cardinality of H, which is 0.405 n. And B is also the same as A, and therefore I take A plus A, which is 2 lambda minus 1 into H. And now something which I am going to use. What is this lambda? This lambda is the number of cosets which A meets. And if lambda is the number of cosets which A meets, the lambda has to be an integer. But also I know the lambda has to be bigger than 0.405 L. Therefore, lambda is an integer and it is bigger than 0.405 L, which means that lambda is actually bigger than the ceiling of 0.405 L. The ceiling meaning which is the smallest integer bigger than or equal to x. Okay, because A meets lambda cosets, and therefore by definition lambda has to be an integer, and lambda is also bigger than 0.405 L, and consequently lambda is just not only bigger than 0.405 L, it is actually bigger than the ceiling of 0.405 L, which is the smallest integer bigger than or equal to 0.405 L minus 1 times h. And that's exactly what we are going to use. By using the star, which is A plus A is bigger than 2 times 0.405 L minus 1 times cardinality of h, we want to get somehow that A plus A is really bigger than 0.595 L. Okay. To start with, we don't know what is the smallest integer bigger than 0.405 L, and therefore I am going to use just the bound 0.405 L only. Therefore, A plus B is bigger than 0.81 L minus 1 multiplied by h, cardinality of h, which is n over L. And when you multiply, you get 0.81 N minus n over L. And this is what I want to be bigger than 0.495. And it's clearly true when L is bigger than or equal to 5. Therefore, for large values of L, I am not going to use all this ceiling, blah, blah. Okay, just it is bigger than 0.405 L is sufficient. But for small values of L, I can use it because I know the L. For example, if L equal to 4, then the 0.405 L will be something like 1.6. But then I am taking the ceiling. Therefore, the ceiling of 1.6 is 2. Therefore, 2 times 2 minus 1, which is 3. Therefore, 3 times h. But the cardinality of h is n over L, which is n by 4, which is also bigger than 0.495. Therefore, if I don't use the ceiling idea, I won't get this. And similarly, for L equal to 3, cardinality of A plus A guy, when L equal to 3, something like 0.405 L is something like a 1.2, and the ceiling is therefore 2. Therefore, again, that gives a 3 to n over 3 to 0.595. But what would happen if L equal to 2? If L equal to 2, then 0.405 times L will be only 0.8. And once it's 0.8 and the ceiling will be just 1, therefore 2 times the ceiling minus 1 is only 1. Therefore, cardinality of A plus A will be bigger than cardinality of H. That's all what I will get. And that I cannot now get 0.595. And that's exactly the reason that for L equal to 2, I am now assuming something more. I am assuming for L equal to 2, the lambda is at least 2. The number of cosets which the A meets for any subgroup of index 2, the number of cosets which A meets is 2. A meets both the cosets. That's exactly what I am assuming. Because if A meets only one coset, I cannot really prove the result. L equal to 2, then cardinality of A is bigger than 2 lambda minus 1 into H. But on the other hand, H is n over 2, and the lambda equal to 2, and therefore you get a 3 times n over 2, which is 0.599. If it were not lambda is 1, then I won't get, I will get only n over 2, which is not really bigger than 0.599. Therefore, that's all the idea, which means that the Ylands theorem, without all this ceiling business, would work for large enough values of L. And for small values of L, that you can use the fact that you have a ceiling and then you can prove it. Okay. And in fact, there are a few more things which probably I will leave it as an exercise. Let me explain them. Therefore, suppose you still want to go, you're still better. We want to have 0.39 N. If A is bigger than 0.39 N, and then you want to essentially say that A plus A equal to G. And then the theorem, again, exactly using Ylands theorem, you will see that the subgroup of index 2 will give you trouble, and the subgroup of index 5 will give trouble, because if the cardinality of A, you are only assuming 0.39n, then it is theoretically possible that your A meets only 2 quasets. Okay, because the subgroup has if the subgroup K is of index 5, then the subgroup has essentially 0.2 times n elements. And if the K has 0.2 times n elements, you can just take only 2 quasets, which will have 0.4 times n elements, and you can just say A to be like that. But on the other hand, in that case, it is not true that A plus A plus A equal to G. Therefore, you have to assume that for any subgroup of index 5, it meets 3 cosets. And you can generalize it, in fact. We will not go into that, but essentially the same thing. If once A is bigger than 1/3, okay, that's a theorem. If A is bigger than 1/3, and if you only for numbers which are numbers L, which is congruent to 2 modulo 3, you have to assume that A meets a certain number of cosets. Once you assume that, then A plus A plus A equal to G. Good. Now, so far, this is additive combinatorics if you want. Now, how are you going to use it? Actually, therefore, let me say that all these things are not necessary for me. What I need is really the multiplicative analog of it. Therefore, now we have been so far writing the groups as an additive groups. I'm just rewriting now the whole thing as in the multiplicative group. Let G be a finite abelian group written multiplicatively. And then, of course, then I want A into A equal to G. And the result that A into A equal to G holds if the cardinality of A is bigger than A over n and A times n. And depending upon the A, I may have to assume that this A meets sufficiently many cosets. Therefore, assuming, for example, if it is 0.41, I have no problem at all. I have to only bother about the index 2 cosets. And if it is little less than 0.4, let's say 0.39, then I have to bother about the cosets 2 as well as 5. And if still I go less, then I have to bother about 2, 5, and 8, and so on and so forth. I mean, assuming I can prove the results for the subgroups of the low index that this A meets all of them, then I will get A into A into A equal to G. And that is precisely what we are going to do. And therefore, this is the first result proved by Riemann and Walker. Let capital Y be Q power 16 over 3. Then the set P1, P2, P3, where every prime is lesser or equal to Y, covers all invertible residue classes modulo Q. Therefore, if you take, okay, P1, P2, P3, where Pi's are going up to Y and Y is Q power 16 over 3, then this covers all invertible residue classes modulo Q. Let me start with an observation. The Y which I am assuming is bigger than Q power 5. Since Y is Q power 5, this result already would follow from the result of Zeta, where he did not even need the 3 prime factors, but he needed only 1 prime factor. But however, the result of Riemann and Walker is true for every value of Q, whereas as we saw earlier, the result of Zeta is true only for when Q is sufficiently large. Okay, that's one thing. More than that, this is the starting point of the investigations. Once you have the starting point of the investigation, then you can try to see whether the 16 over 3 can be improved to less than 5, and therefore won't follow from Zeta's result. And that, as we saw, is exactly what happens in the Linnick results. Linnick proved that there exists a constant, and initially it was 10,000. And then, of course, that was the first step. He showed an idea how to do that. And then it continued, and then finally we will get even up to 5, even though we expected 2 plus epsilon. Okay, therefore let me prove this theorem. Therefore, we have to prove that if you take P1, P2, P3, where Pi is less than or equal to Y, where Y is Q power 16 over 3, then this product covers all residue classes. Okay, this is the idea. Let G be the group Z over Q Z star. This is the group which I am going to do, and that is exactly the reason why in the combinatorics I really wrote it in terms of the multiplicative rather than additive. But I started with additive. I started with additive because in the literature, when you go through these things, in the literature, it is always written for an additive group. And therefore, whenever you need the result for a multiplicative group, you have to sort of change the language. Okay. Therefore, let G be the multiplicative group, Z over Q Z star, and P be the primes P less than or equal to Y, P not in Q, and A is the projection of this P in the group G, which means that I take every prime P congruent less than or equal to Y and read it modulo Q. Okay. Therefore, that's a projection. Therefore, I read it modulo Q, and that is by A. Now I use the multiplicative version of the theorem. And suppose I can prove two things. Number one, cardinality of A is bigger than 0.41 times PQ, because PQ is the order of the group. And suppose I can meet A meets every coset of index 2 subgroup H. And then by the theorem, it will follow that A dot A equal to G. And if A dot A equal to G, that simply means that there exists a prime P1 in A and P2 in A and a P3 in A, such that P1 times P2 times P3 is equal to G. Therefore, given any element G in G, I can find out primes P1 in A, P2 in A, P3 in A, so G is equal to P1 times P2 times P3, and that's exactly what I have to prove. Therefore, as I was telling earlier, therefore we see that somehow the combinatorial, once you have 3 primes, then the combinatorial methods can be brought into play, which is not very clear if you are having 1 or 2 primes. If you are having 1 or 2 primes, it seems to be only analytic methods will come. Okay, therefore our thing is cut out. I need to somehow prove that the cardinality of A is bigger than 0.41 PQ, and I also have to prove that A beats every coset of index 2. Now, we are taking my P to be primes up to Y, and that is around Y over log Y by prime number theorem. But now I don't take all primes. I'm taking only primes which do not divide Q. But on the other hand, the number of primes which divide Q are very small, and therefore that won't matter. And therefore, the P is still of the order Y over log Y. And now every reduced residue class contains at most L elements where L is equal to 2 times Y divided by phi Q times logarithm of Y over Q, which is precisely the Brute-Titmarsh theorem which we saw. The Brute-Titmarsh theorem says that every residue class will contain at most 2 times Y by phi Q times logarithm of Y over Q. You would expect that everything will contain Y over phi Q log Y, because by the prime number theorem, but on the other hand, we saw that it is not true, but the result which we get is weaker in 2 respects. You get a constant 2 as well as the log Y being replaced by log Y by Q. And now the choice of Qy is equal to Q power 16 over 3, and therefore Q is Y power 3 over 16. Therefore, instead of Q, now you put Y power 3 over 16 and then simplify, you get 13 over 32 times Y over phi Q log Y. And 13 over 32 is bigger than 0.4. It's not, when I have written 0.405, that is not true. It's strictly bigger than 0.405. And that's exactly what I want to prove, that A occupies at least those many cosets, which means that the cardinality of A is at least as big as 0.405. Okay. Therefore, this is essentially the Ylands theorem and Brute-Titmarsh. Brute-Titmarsh says that every residue class will contain only a few number of primes. And once that is true, therefore this A happens. That's all we are using. Just Brute-Titmarsh, that you know the number of primes is of course up to Y over log Y, but every residue class will have only 0.4, at most 13 over 32 Y over phi Q log Y, and therefore this A has to cover at least these many residue classes, which means that the cardinality of A is bigger than this. And the only thing, next thing which I want to prove, as we see here, that A meets every coset of index 2 subgroup. Therefore, what is A? You start with the primes P, all the primes up to Y, and take the projections onto Q, and then that group meets every coset of index 2, which is essentially saying that the P meets every coset of index 2. If P meets every coset of index 2, then of course A will beat every coset of index 2 because you are only projecting it. And that's the theorem which you want to prove. let P be a primes all less than 25 Q square, which is much better than what we want. We want Q power 16 over 3, but I'm just taking much smaller number because of the usage for future. Then P bar meets both the cosets. P bar is essentially the projection of H for any subgroup H of index 2. Therefore, I take a subgroup H of index 2 and I take all primes up to 25 Q square. And then I want to say that when you take all primes up to 25 Q square, it meets both the subgroups of index 2. Let's give a sketch. A subgroup H of index 2 can be viewed as a kernel of some Dirichlet quadratic character, which probably most of you see. I mean, you know Dirichlet characters, and take a quadratic character, and then they take the kernel, and that's what any subgroup will look like. Therefore, it is sufficient to prove that this chi, this character, takes the value +1 as well as -1, evaluated at p less than or equal to 25 Q square. Therefore, I just take what I have to finally prove is that I take all primes up to 25 Q square, and then I take a Dirichlet character, quadratic character, and then I want to say that this quadratic character takes both values +1 as well as -1 when I take all the primes up to 25 Q square. Suppose not. Suppose chi p equal to 1, not only even up to 25 Q square, up to for primes up to Q. If chi p equal to 1 for primes up to Q, then chi n equal to 1 for every n, which means that chi is a trivial character. Because chi, the Dirichlet character, as you know, is actually periodic modulo Q. Therefore, what happens up to Q is what matters. And once up to Q, you know what happens, then of course, because of periodicity, that's exactly what would happen everywhere. And if up to Q, the value is 1, then of course the value will be 1, except for those numbers which are co-prime to Q, except which are not co-prime to Q, but that's okay. Those things you know. Therefore, the chi is trivial. Suppose chi p equal to -1, which is same as mu p. Then if chi p behaves like mu p for all primes up to 25 Q square, then L1 chi will behave like a zeta 1 over zeta 1, because LS chi will behave more like a mu p product of 1 plus mu p by p power s, and that would be essentially 1 over zeta s, and therefore that will behave like a 1 over zeta 1, which means that it will be very small. That's what that is not something which is difficult to prove, that if chi p equal to -1 for all small values of p, then L1 chi is very small. But that would contradict the known lower bounds for L1 chi. We know various lower bounds for L1 chi, and you can use that, and that contradiction would essentially prove that it is not possible for chi p to be -1 for all values. Therefore, the chi takes both values -1 and +1, which essentially means that if H is any subgroup of G, G is of course the set over Q star, and if H is any subgroup, and if it's of index 2, then the primes up to 25 Q square would meet both the cosets of H. There will be some elements, some primes which will be in H, and some primes which will be in H complement. Therefore, all the primes being only in H or all the primes being only in H complement will not happen.
I hate to interrupt, Professor Balasubramanian.
Yes.
You have about 3 minutes left.
Okay.
And then we'll take some questions if you don't.
Yes. Okay, that result was improved to Ravarai, Srivastu, and Oriel Serra, who proved that y equal to 650 Q cubed is permissible. And since I don't have much time, let me just explain what's going on. Here, the idea is to get a variation of the Brute-Titmarsh theorem to improve the lower bound for A. Therefore, recall P is equal to P less than or equal to Y, and let GT be the characteristic function. Now, suppose we count primes not with the weight G, but with the weight G convolution G, and a slight variation of G convolution G, and then you will get this eta t to be like that, and then you take the weight, and then the number of your primes up to y with that weight is y over 2 log y. But what is more important is now we count not only the primes which are congruent to A modulo Q, but in fact we take a subgroup H and take the cosets, and then we count the number of primes in the coset itself, which is much better than counting each element and then multiplying by the number of elements in the coset. Just the coset itself you take. and therefore let UH be a coset of H, then one can prove that the number of primes in a given coset is less than 1.2485 divided by L log Y. And if I don't do that, and if I do the standard Brundt-Marsh, then the number of cosets is phi q over L, number of elements in a coset is phi q over L, and then you'll get a Y over phi q to log Y over Q. Remember, I have not put the 2. I have not put the 2 because the 2 will disappear when I put the weight. I'm counting with the weight 2, eta, and once you count with the weight eta, then you won't get the 2, and that will give you 1.5 times Y over L log Y, and that is not good enough for us. I need something like less than 1.25. And once you have that, then you can actually prove that A meets at least 0.4 L cosets, and therefore 2 is the only one which gives trouble, and then there's no problem. 2 we have already checked. And I have just given the proof, which I don't bother. And then the work in progress is it can even take 30,000 cube power 5 over 2 is admissible. And I will just take 2 minutes to explain what's the basic idea. The idea is to do again the Brundt-Marsh. And the Brundt-Marsh, what we prove is, Brundt-Marsh with an appropriate weight eta. Now the eta is a triple convolution of the characteristic function. Earlier we had a double convolution. If you take a triple convolution, then you get a 4 over 9 into x into 1.004 times epsilon a by phi q into logarithm of u over 10 power 11 square root of q, where for this epsilon a, I don't have an good L infinity norm, but I have a good L2 norm. And therefore that enables you to throw away the epsilon a. And this is something which I wanted to explain. Unfortunately, I don't have time. And this is essentially by using what is called Selberg-C. And in fact, if we already start Selberg-C, that will take time. But then anyway, I will stop here.
Well, thank you very much, Professor Balasubramanian. Thank you.
Sure.
Oh, nice talk.
Yeah.
Very exciting. Are there any questions? Do people have questions?
Yes, I have one question.
Yeah.
So why the product of 3 primes are so important? Is there any generalization of this result for n product of n primes?
Yeah, we can actually do that. I mean, the same method. You see, the whole idea essentially of Ramaray and Walker is that if you don't take 1 or 2 primes, more primes, 3 or more primes, then combinatorial methods can be made into play. Okay, and then what we were trying to see is what the best that you can take the juice out of this combinatorial method. It is also would be interesting whether this combinatorial method can be somehow combined with the analytic methods to get something, which I have been thinking with no real clue of how to do that.
Okay.
But other the same method, because from 3 or more primes, of course, the combinatorial method as on today seems to be giving much better results than the analytic methods. But probably there may be a way of combining both. I have been thinking off and on, but I have no real clue how to do that.
Okay. Thank you.
Okay, good. Are there any other questions?
Yeah, can I ask one more question?
Yeah.
So, in the continuation of his question, there is one thing that suppose I have only one prime I am dealing, that where the more difficulty looks like, because I don't have more of this size of A plus B type of results. But
No.
why it is more difficult in case 2 also?
Essentially because we don't have the A plus B type thing, therefore there is no way combinatorial methods can be made to play. It's only the analytic methods. And as you know already in the analytic methods, the exceptional zeros gives you all the trouble. And therefore you need really a good estimations. I mean, that is something again which was started by Heath Brown, I think, who proved 5.5 with the various innovative ideas. And then he also explained how the results could be improved. But even then, I mean, going anything beyond 5 is going to be very difficult, essentially because of the numerical estimations. Numerical estimations are not easy in this case. I mean, we don't have any other method. Just you have the standard, the Linux, the method which was developed by Linux, except that you have to do the estimations a little carefully for L functions.
Also, can you explain this eta function little bit, how it comes? And it was in the last slides, the eta function was defined a little bit.
Oh, okay. You want to see that? Okay,
Yeah, and
no. Okay, the whole problem essentially is the thing that, you know, this is a remark I think the Peters have not made once, I think. Okay. Anyway, suppose you have a sum f of n goes up to x. And if you have a sum f of n goes up to x, and then you have an arithmetic formula, and most of the time you are able to get a good O result and actually a good omega result. And the fact that you are able to get an omega result is not too surprising, essentially because you are summing f of n over the interval 1 to x. And the characteristic function of 1 to x is 1 from 1 to x and 0 immediately. Therefore, this is a discontinuous function. But however, if you really approximate this discontinuous function, namely the characteristic function of the interval 1 to x, by another C infinity function, then the error terms become small. And not only that, you can't easily prove such an omega result, because if the original functions which you are adding is a smoother and a smoother function, then most likely you will get a good omega result, good O result, and you will get a bad omega result, because the smoother functions, the O results will be very good. And that's basically the idea. See, originally we were Brute, Titmarsh, etc. is summing primes up to y. Okay, with a weight 1, with a weight which is the characteristic function. The rather we can put this way, that you are summing the primes, summing over the primes with the summand being the characteristic function of 1 to y. And that is the characteristic function of 1 to y, as I was telling you, is a discontinuous function. Suppose instead of summing up like that, but instead you sum over little smoother functions, then you should be able to get much better. And the smoother function which we normally take, which you probably would have seen already in many examples, is given by the convolution. Therefore, you take the g as the characteristic function of 1 to y, and then take the convolution, 2 times convolution or 3 times convolution, and then sum that up. And then you get estimates which are much better. But except for the fact that if you take more and more convolution, then the calculations becomes more and more difficult. Okay, and that's exactly. But now that you have asked me, therefore, what happens is that you have a. Let me explain this calculation, for example. Yeah. Okay. For example, you are summing over here. For example, that you are summing p over y with an eta belonging to the residue class belonging to the coset UH. When you are summing over P belonging to UH, even with the weight, it is not easy at all how to do that. And therefore, the only way probably which we can do, which is what we have done, is essentially use the Selberg's idea. Therefore, you just put a kernel d dividing n lambda t whole square. Here, lambda 1 equal to 1 and lambda d equal to 0 for Lie, because I said, as all of you might have known. Therefore, when n is a prime, then, okay, ignoring n less than z, because that won't matter. Therefore, when n is a prime, then the sigma d dividing n lambda d is actually just lambda 1 alone, because the other one will be lambda n, and lambda n will be bigger than z, and therefore that will go away. And therefore, this weight which you have put is exactly 1. Oh, sorry, equality I have written, it should be less or equal to. But on the other hand, it doesn't really matter for other n's, because what you have put is a non-negative number, and therefore that is perfectly okay. And then you use the Selberg's thing, and then you do the things. And that's, in other words, once you put a kernel like eta and things like that, then it doesn't seem to be easy, just as it is to get an asymptotic formula or anything like that. Therefore, the primes have to be handled. And the one easy way to handle the primes is essentially this Selberg's thing. Okay. That's exactly what we are doing. That instead of summing over with a weight which is the characteristic function of the interval, you just approximate the characteristic function of the interval by some C infinity function, and then try to sum it over that C infinity function. Then you hope to get much better result.
Thank you.
Okay. Look, if people want to continue chatting, that's fine. I guess I should say that the lecture is in some sense officially over, but people are having so much fun discussing this that maybe we should just let people
I
chat.
think that this next lecture starts when?
10 minutes, 10:10.
Okay.
Sorry, 11:10. So
Okay.
let's just say it's
11:10.
officially over, but people should be encouraged to chat, okay?
Yeah, sure.
And how's that? Is that all right?
Yeah, sure. If anybody asks anything more, I will be happy to answer.
Please, people should be encouraged to ask if they have questions.
Yeah.
If not, then I thank Professor Balasubramanian for an excellent talk and a nice discussion. And we shall continue in about 10 minutes. Okay? Thank you so much.
Thank you very much.
Hello.
Hello.
Yeah, yes, sir.
Hi.
Hi, sir. Good
Is
morning.
it Palla?
No, it's Manish actually.
Oh, hi, Manish.
Yeah. Yes, sir. So you can share your screen.
Sure, sure.
Yes. Yeah. Yeah, it's visible.
Yeah.
Yes. Yeah. Can you make it
Professor
slightly
Deutsch?
full screen?
Yeah, yeah. Hello, Professor Deutsch.
Professor Atul Dixit, how are you?
Yeah, I'm doing good. How about you? Yeah.
Pretty good, pretty good.
Yeah. Nice to see you after 1.5 years. Yeah. So.
Well, I'm glad, to see each other, even if it's only via Zoom.
Sure.
So you have something very interesting for us. Good, that's good. Okay. Should we begin, or
Yeah.
maybe we should wait one more minute?
Okay. Sure.
You'll have to tell us where you found this this work.
Yeah, I am going to say a few, few slides about this. Yeah.
Very good, very good. Oh, wow. Okay. Are you able to get around much, or are you stuck at your home institution, Professor Dixit?
So we can go outside. Last week, actually, I made a first trip after my SRM trip 1.5 years back to Pune. So it's in Maharashtra. So it was only for a day. But other than that, I haven't traveled at all. So, I mean, within my city, yes, I have, but not outside.
I did an intercity travel a couple of weeks ago,
Okay.
but I needed special, electronic, passport to get into Tamil Nadu. I mean, it was just weird. But it was quite exciting. Okay, so I guess it's time. Let's begin. For our second talk, we have a speaker who has previously graced us with his presence at the mathematics seminar of SRM University, AP. Professor Atul Dixit will be speaking on Koshlyakov zeta functions and modular relations. Without further delay, here is Professor Atul Dixit. Professor, please.
Sure. Thank you very much, Professor Deutsch, for a very kind introduction. I still have very fond memories of my visit to SRM in March of 2020, days before the pandemic started. So good morning to all of you. So today I'll be talking on a joint work with my PhD student, Rajat Gupta, on Koshlyakov zeta functions and modular relations. So let me first give a short table of contents. So I'll be saying something about how how we unearthed Koshlyakov's manuscript. It will be a personal story for a few slides, and then origin and contents of the manuscript, followed by the theory of Koshlyakov zeta functions, a brief description of it, and then new results that we have found in this theory, and then some future directions for further work. So let me start from how Lost Notebook of Ramanujan was unearthed. So the discovery of Lost Notebook, which is 138-page manuscript along with some loose papers which Ramanujan worked on the last year of his life, it has been compared to the discovery of Beethoven's 10th Symphony. So this Lost Notebook of Ramanujan was discovered at the Trinity College Library at Cambridge in 1976 by George Andrews of Pennsylvania State University, almost 56 years after the death of Ramanujan. And we know Lost Notebook has been so useful and is being so useful in so many fields of mathematics as well as outside of mathematics. Leave aside just in number theory and analysis. For an example, I would just like to give one function of Ramanujan, the Mach theta function, which has seen a lot of applications in the last decade in areas as diverse as string theory, black holes, etc., etc. So I'll be talking about a similar such discovery, though not as something phenomenal as Ramanujan's Lost Notebook, because Ramanujan's Lost Notebook was never published before Andrews found it. This one is published, but is not known at all to the mathematical community. So part of the reason of giving a talk on this work of Koshlyakov is to pay a tribute to him and to also say how important piece of work it is. Okay, so another thing, Koshlyakov's manuscript. So while I was a fourth-year grad student in 2010, I came across a survey article on the work of Russian mathematician Nikolai Sergeyevich Koslyakov. This article was written on account of his birth centenary. Here is a photograph of Koslyakov lecturing. He made some seminal contributions in number theory as well as in differential equations. For example, I'm conversant only with his work in number theory, but in differential equations also he has worked a lot. His book, Principal Differential Equations of Mathematical Physics, is quite famous. So I was reading across this survey article and I came to know that, okay, there is some stuff given in there which seems to be related to what I was doing in my PhD thesis. And so I was at the same time happy as well as disappointed. Disappointed because I was curious to see whether there was something in there which might be something I was working on. Fortunately, there was no overlap in what he had done and what I was doing. And so I was quite happy. But I was also very happy because of one interesting piece of information that I came across. So let me say about that. So there is one paragraph given in this manuscript, which I will read out. It's very important and also very motivational. So for all of us. So the paragraph is like this. The repressions of the 1930s, which affected scholars in Leningrad, continued even after the outbreak of Second World War. In the winter of 1942, at the height of the blockade of Leningrad, Koslyakov, along with a group, was arrested on fabricated dossier and condemned to 10 years correctional hard labor. After the verdict, he was exiled to one of the camps in the Urals. On the grounds of complete exhaustion and complicated pellagra, Koslyakov was classified in the camp as an invalid and was not sent to do any of the usual jobs. Very serious shortage of paper. He was forced to carry out calculations on a piece of plywood, periodically scraping off what he had written with a piece of glass. Nevertheless, between 1943 and 44, Koslyakov wrote 2 long memoirs, and I'll read only the English translation. I'm not able to read Russian. A study of some questions in the analytic theory of rational and quadratic fields, and a study of a class of transcendental functions defined by the generalized Riemann equation. So if you read further in that article, it is said that his son, who is also one of the authors of that article, before his family and him was taken away from Koslyakov, and Koslyakov was put in jail, he had an idea of giving Koslyakov all of his papers that he had written up to that time, as well as the book, A Course of Modern Analysis by Whittaker and Watson, a very famous book. So the first memoir, this one here, a study of some questions in the analytic theory of rational and quadratic fields, after it was written, was lost in transit, so from jail to the mathematical community. However, we believe that Koslyakov reproduced this work in 3 papers he wrote after he was released from jail. So if you see N.S. Koslyakov, this investigations of some questions of the analytic theory of rational and quadratic fields, parts 1, 2, and 3. The titles appear to be same. And the year is 1954, which is about 5 years later when he was released from jail. But this is not the one that I'll be talking on. The one which is titled A Study of Class of Transcendental Functions Defined by the Generalized Riemann Equation is what I'll be talking about. So it so happens that when Koshlikov sent his manuscript to Stekelov Institute of Mathematics from jail, it went into the hands of Vinogradov, Bernstein, and Linick. We heard about Linick in Professor Balu's excellent lecture just before my lecture. So these three people were so impressed by the contents of Koshlikov's manuscript that they immediately recommended its publication. However, because the then ruling NKVD party did not want to have the name of the mathematician in its actuality, seeing that he was a mathematician who was put in jail, they asked him to put a different name. And so if you see Koshlikov's name does not appear as the author of this manuscript, it goes by name of N.S. Sergeev or Sergeev. So his name was Nikolai Sergeyevich Koshlikov. So he made a very nice decision to include his patronymic name there, the name of his coming from father, as N.S. Sergeev. Anyway, so I came across this interesting piece of information from this article, and then the next big task was to try to obtain a copy of it. Unfortunately, it was not very difficult because the math librarian at University of Illinois, Tim Cole, told me that the Center for Research Libraries in Chicago has a copy of it. And the CRL was kind enough to scan this 150-page manuscript and email it to me back in 2010. So here is a picture of the first page of the manuscript. As you can see here, perhaps we can make out the word Stekelov. So it was published by the Stekelov Mathematical Institute. And you can also perhaps guess from here that the last name is Sergeev, as I said. It was N.S. Sergeev. This is the title, a study of a class of transcendental functions defined by a generalized Riemann equation. And we can say that it was published in 1949 in Moscow. Okay, so from 1949 to 2010, until I found about it and got a copy of, this was a published manuscript. But for 61 years, there was not even any mention. There was one mention about it, and we found about it only last year when my student Rajat and I decided to work on it. So there was only one reference to this manuscript in a PhD thesis of somebody called Kisunko, where on page 4 of that thesis, he just says that, okay, what are various generalizations of the Riemann zeta function? This is one such. The Koshlikov, he doesn't say as Koshlikov zeta function. This is something that we coined. But he has only the definition of one of the two zeta functions. But he doesn't work at all on the zeta functions of Koshlikov. So last year, we decided that it would be a good idea to try to see what is there in the manuscript. And my student kindly translated this manuscript from Russian to English. It was a huge task because it was 150 pages long. So even though this manuscript got published in 1949, the churning of the concepts in this manuscript starts revolving in the head of Koshlikov right from 1930s. As you can see from two papers that he had published, one in Mathematische Annalen and the other in Sbornik Mathematics. So this is in 1923 and 1935, and you can see glimpses of what is going to appear later in full-fledged manuscript in 1949. The genesis of this manuscript is a problem in physics in the analytical theory of field distribution. So let me go over it briefly, although I'm not good in physics. I'll try to give a motivational introduction to this. So if we consider a sphere of radius R2, suppose the radiation occurs on its surface, R equal to R2, into a medium at a zero temperature. So initially we have 0 temperature. Suppose the initial temperature is U equal to 0, the heat sources are placed on the spherical surface of radius R1, where R1 is strictly less than R2, and the rate per unit time of heat propagation from the whole surface is Q. Then the problem is concerned with finding the temperature at time t greater than 0. So if K is thermal conductivity, H is the emissivity of the surface, and the specific heat is C, with rho being the density of the material forming the sphere, then the relevant form of heat equation turns out to be this. So we all know the heat equation has this form, and with these initial conditions. So the temperature being 0 initially, and then we have also this particular condition. Now, this thing occurs in that paper that I said, one of the 2 papers which he worked on before this manuscript. The paper is titled An Extension of Bernoulli's Polynomials. And in there, this particular equation is given. The solution of heat equation we all know is Jacobian theta function. So in this generality, it turns out to be a generalization of the Jacobi theta function. And this is where Koshlikov really begins and then develops this beautiful manuscript. So by separation of variables, one can actually see that the characteristic solution of this above system turns out to be this: mu cos mu plus p sine mu is equal to 0, where p is in terms of this radius of the sphere R2, and h being h over k, where h is the emissivity, small h, and k is the thermal conductivity. So mu is the eigenvalue, okay? And this is the equation which is the crux of Koshlikov's theory. Okay, so let me now move on to what is there in Koshlikov's theory. But let's begin with a brief, very brief introduction to the theory of Riemann zeta function. So for real part of s greater than 1, the Riemann zeta function is given by this absolutely and uniformly convergent series, summation 1 upon n to the power s. It can be analytically continued to the entire complex plane except for a simple pole at s is equal to 1. Riemann himself gave a beautiful functional equation, which is completely symmetric. This part is symmetric as we go. I mean, if you just replace s by 1 minus s, we get the same thing. And this is the asymmetric form of the functional equation. Zeta 1 minus s is 2 times 2 pi to the power minus s, gamma of s zeta plus times cosine pi s by 2. Okay, so let me now begin with what Koshlikov had in his mind. So around 20s, there were a number of papers by German mathematician Hamburger, who sort of provided the first inverse theorem for the Riemann zeta function. So the theorem is like this. If we have 2 Dirichlet series, f of s given by summation a of n over n to the power s, g of s given by summation b of n over n to the power s, where both are convergent for some half plane, let's say for large real power of s. And if f is a meromorphic function of finite order with finitely many poles, so s minus, let's say if it has a pole at s is equal to 1 of order m, then s minus 1 to the power n is a function. And let's say we have finitely many such poles. Okay, that is the only condition. So meromorphic function of finite order with finitely many poles, which satisfies this functional equation. So f and g satisfies this functional equation. Then f and g have to be some constant time the Riemann zeta function. So we all know what the Bohr-Mollerup theorem is, right? A characterization of the gamma function. If we have gamma of, let's say for time being, let us consider gamma at real arguments, gamma of x, where x is something from 0, infinity to 0, infinity. And if we have gamma of 1 equal to 1, gamma, if we start with f like this, f of x, where the domain is 0, infinity, range is 0, infinity, f of 1 is 1, f is logarithmically convex, and f of x plus 1 is x times f of x. Then f has to be nothing but the gamma function. This is the Bohr-Mollerup theorem, and it has its generalization for complex variables, which is known as Ylands theorem. A similar thing was given by Hamburger in the case of the Riemann zeta function. So if you have 2 Dirichlet series with this condition on f and this functional equation that they satisfy, then f and g cannot be anything but a constant times the Riemann zeta function. So essentially the Riemann zeta function. Initially, Hamburger starts with f and f here, and then he says that, okay, then you can go over to G, where G would look like, I mean, G of 1 minus s would be summation A of n over n to the power 1 minus s. And then he says that, okay, it need not be A of n, you can even start with any B of n. Yet you will get f and G to be equal to C times zeta. So this forms the beginning of Koshlikov's idea. Because what happens is that Hamburger later wrote a series of papers where he studied more general functional equation of this type, where now f is a Dirichlet series, but G is not necessarily so. I mean, if we impose that G also be a Dirichlet series, and then if we have this condition about f being a meromorphic function with finite many poles for finite order, then there is nothing to study, right? By Hamburger's theorem, they both f and G have to be some constant times Riemann zeta function. But if we relax that argument, let f and G satisfy this functional equation, but have one of them to be a Dirichlet series and the other not necessarily so, then Hamburger studies analytic properties of these functions, but unfortunately, he doesn't give any explicit example of such pair, f and G. Now, let us see that this is somewhere in 20s and 30s, right? Hurwitz, as early as in 1891, wrote a thesis on Hurwitz's zeta function. So if you look at Hurwitz's famous formula, zeta of 1 minus s comma a is 2 cosine pi s by 2 gamma of s 2 pi to the power s times this part. I have written it in a slightly different language because I wanted to emphasize upon this factor here, which is the same as what appears in Hamburger's functional equation. So Hurwitz's zeta function was already there in as early as 1891, right? It's about 40 years earlier. So isn't this an example of what would constitute Hamburger's functional equation, I mean, solution to Hamburger's functional equation, where you have f to be this zeta, Hurwitz zeta function, G to be this particular thing, and this is not a Dirichlet series because in the top you have this something which depends on S. But so this could be an example, but the thing to note is that this is only valid for real part of S greater than 1, or you can also go up to real part of S greater than 0 if you do not assume A to be equal to 1, right? So it's only in some half plane. It's not for all complex values of S. So what would be an example about, I mean, what would be an example of a pair which satisfies Hamburger's functional equation and of which one is a Dirichlet series, the other is not? So that was what Koshlikov thought of, and he gave the first example of this in his manuscript. This is also, even though it comes from something that he does before, I mean, bits and pieces, these zeta functions only appear in his manuscript, which was published in 1949. So we call these zeta sub p of s, you can take this to be f, and eta sub p of s to be g as that pair. So these are what we call as Koshlikov's zeta functions. One of them is the Dirichlet series, the other is not. You can see here the dependence of the numerator on s. And this particular expression is defined by 1 upon gamma of s times this integral. What are these lambda 1, lambda 2, lambda 3? They are solutions of the positive real roots of the characteristic equation. So this is the equation, very similar equation appeared before. In fact, if you replace in here lambda by mu over pi and p by p over pi, you'll get back to the previous equation that he studied some years before. But now he gets this idea that, okay, if you look at these roots of this characteristic equation, remember the one that I showed using the separation of variables. And if you take these real roots of these positive real roots, and then you form this Dirichlet series, and then you put that in the functional equation of Hamburger, and then you try to see what the other one turns out to be. It turns out to be this one. And then he develops from here the complete theory of his zeta functions. Now, interesting thing to note is that if I take this particular characteristic equation, divide both sides by p, of course, p is greater than 0, and I let p tend to infinity, then you see this thing drops out. you just get sine of pi lambda equal to 0. So what are the roots? The positive real roots. They will be nothing but the positive integers. And so here you will be putting 1 to the power s, 2 to the power s, 3 to the power s, and so on. And here, if I divide the numerator and denominator by p square and let p tend to infinity, this just approaches 1. So what you get is the Riemann zeta function, zeta of s. Similarly, if I go with eta sub p of s and I let p tend to infinity, then let us observe here. The new here is 2 pi p. So I put 2 pi p k minus x over 2 pi p k plus x whole to the power k. If I divide the numerator and denominator by 2 pi p, then I see that this thing approaches 1. And if I look at the integral representation of the gamma function, because we have real part of s greater than 1, 0 to infinity e to the minus x times x to the s minus 1. That is nothing but gamma of s. So gamma of s divided by gamma of s, that becomes 1. So again, the numerator here also becomes 1, and you have k to the power s. So it becomes the Riemann zeta function. So in the case when p tends to infinity, both reduce to the Riemann zeta function, and you can see that the lambda j's are nothing but j, the positive integer. What happens if p tends to 0? You'll see that the lambda j's, because see, this is 0, and so lambda cos pi lambda is equal to 0. What are the solutions of this? We don't want lambda to be equal to 0. It's just a 0 solution. So the roots of cosine, and they will be at 2j minus 1 upon 2, right? Where j is any positive integer. So nothing but j minus half. So lambda j's tend to j minus half. And in this case, what do these two functions reduce to? They reduce to, again, this factor 2 raised to s minus 1 times zeta of s and 2 raised to 1 minus s minus 1 times zeta of s, respectively. So again, you get back Riemann zeta functions, essentially. But now, for any other value of p between 0 and infinity, you will get lambda j's to be between j minus half and j. And these will be something which do not reduce to the Riemann zeta function. So Koshlikov's zeta function theory involves, as a special case, the theory of the Riemann zeta function. So let us see how far we can get, how far Koshlikov worked on in this theory. It's an amazing work where we have a lot of things. Imagine something about 150 page long, and something which is written in jail under extreme hardships. So that is another very important part of it. So Koshlikov showed that both these zeta functions can be analytically continued in the entire complex plane, except for a simple pole at s is equal to 1, with residues being 1 and 1 over 1 plus 1 upon pi p, respectively. So again, if I let p tends to infinity, then this becomes 1. You get, because this becomes the Riemann zeta function. If p tends to 0, then what does this become? The residue becomes 0. Okay, because you see that here, this eta sub 0 of s, if I may call it by that way, it doesn't have any, so the residue is 0 at that point. Okay, so of course, these two satisfy this functional equation. This is also shown by Koshlikov. And with this setup, he constructs this complete theory, not only of the zeta functions, but of course, if you are developing the zeta function theory, there are a number of associated functions that you have to deal with. And there is theory of gamma functions, the generalized gamma functions, which he calls as gamma morphic functions. There are 2 of them. See, there are 2 zeta functions, there are 2 gamma functions, there are 2 Euler constants, there are Bernoulli polynomials. I'll say why not 2, somewhere towards the end of my talk. Generalized theta function, as I said, the solution of the generalized heat equation that he formulated. Generalized Hurwitz zeta functions, again, there are 2. Not only that, there is a complete chapter on summation formulas. He gives a generalized Poisson summation formula. He gives a generalized Abel-Plana summation formula. There is also one chapter, the last chapter, fully devoted to some modular equations that were studied by Ramanujan and Koshlyakov and Hardy. The generalizations of them in this theory. Actually, not of Koshlyakov, just of Ramanujan and Hardy. Let us briefly see what all things we have. So I think I have, Professor Deutsch, I have until 12, right? So 22 more minutes, if I'm not mistaken.
Yes.
Okay, thanks. So let me briefly say, the Lorentz series expansion of zeta sub p of s has as its constant term this first extended Euler constant. The residue here is 1 at 1. And this is the definition of the extended Euler constant. Eta sub p also has a pole at s is equal to 1. But as you can see, the residue is 1 upon 1 plus 1 upon pi p. Here is the constant term. The constant term is in terms of this extended second Euler constant and this q function, which is nothing but the incomplete gamma function. Okay. There are two gamma functions, the generalized gamma functions, which he calls as gamma-morphic functions of the first and second kinds. So here is the first one. Here is the Weierstrass product for gamma 1 comma p of x. If p tends to infinity, you will see that this and Cp of 1 reduced to gamma of s and the Euler constant respectively. He studies the logarithmic derivative of this first gamma-morphic function, and this is how it has as its series representation. I mean, the one for just the digamma function is familiar, right? Minus gamma and then minus 1 by x times this series where you don't have this part. And there, instead of lambda j's, you have just j's. There is an integral representation which will be instrumental in one of our results. So this integral representation for this minus all of this. And this is nothing but something which involves this sigma of t, which is p plus t over p minus t. So when p tends to infinity, this becomes just 1. Okay, and so you get back the familiar formula for psi of x. The second gamma-morphic function has this Weierstrass product. Let me not go into this detail of what this definition is, but it is there in the manuscript. If p tends to infinity, again, I should have had here 2 and 2, both reduced to this gamma of s and Euler constant. Again, there is analogous psi 2 comma p of x and this representation, which again will be instrumental. But now here, if you see, this one is defined by this series. Now, if I let p tends to infinity, this just becomes 1. This lambda j has become j, and you get back the 1 upon e to the t minus 1, the familiar one which is there in the definition of the integral representation of psi of x. Okay, so let me go back to the functional equation. What he does is he also gives a symmetric version of it, and the symmetric version can be achieved if we define this omega sub p of s to be the average of these two zeta functions, zeta sub p of s plus eta sub p of s over 2. So remember that eta sub p is not a Dirichlet series. So even if real part of s is greater than 1, we cannot write this in the form of a Dirichlet series. And hence, omega sub p of s can also not be written as a Dirichlet series. This imposes a lot of restrictions in what we try to do later. So in this, if you make this as the definition, then this asymmetric form of the functional equation can be put in this beautiful symmetric form. And as I have said earlier, when p tends to infinity, this is nothing but zeta of s, because this both becomes zeta of s. And if p tends to 0, this becomes this factor times zeta. Okay. So what about the Riemann psi functions? There are analogs of these also in Koshlyakov's manuscript. So let me first say that in the Riemann psi function, psi of s, it's the functional equation part times this s minus 1 by 2. And this makes it to be a nice entire function. And when we evaluate it on the critical line, then we call it as cap c function of Riemann. This is psi of 1/2 plus i. There are some modular transformations in the work of Ramanujan and Hardy. The first one is from a paper of Ramanujan. This is the one. It's very nice. And recently, in another work, we also had it instrumental in one of our results. In fact, a generalization of this that we needed. So both these modular transformations come from this integral involving this Riemann psi function. You just replace alpha by beta in here. I mean, beta is pi over b. So if you, sorry, not beta, b. And I'm keeping on, I keep on saying this alpha and beta, a and b. So if I put instead of a, pi over b, then you'll see that you'll get back the same thing. And so this one becomes exactly equal to this. There is another modular transformation due to Korshlakov in the last chapter, which generalizes this modular transformation on Ramanujan that I showed you on the previous slide. So in fact, it involves this xi sub p of s and xi sub p of t. Like psi of t, this is also even for even values of t. Okay. And again, ab equal to pi, and you have a beautiful symmetric modular relation between these two integrals. And they come where we put this p in here, and except for this psi sub p, this all is the same. Okay, there is one more result related to a formula, such formula of Hardy, but I'll skip that. Let me go to page 220 of Ramanujan's Lost Notebook. On the middle of this page, Ramanujan gives an elegant modular relation involving the digamma function, gamma prime of x over gamma of x. So this is how it is. So if I define phi of x to be psi of x plus 1 upon 2x minus log x, and then I have this beautiful modular relation. Now here alpha beta is equal to 1, and both are equal to this particular integral involving the Riemann psi function. Now, I'll say briefly how this formula makes sense. So first of all, we are creating this infinite series out of these functions. If you look at the asymptotic expansion of psi of x as x tends to infinity, then you'll see that the first two terms in its asymptotic expansion turn out to be minus 1 by 2x and plus log x. So if you take those on the left-hand side, so that will form this function. So this function has, as its asymptotic expansion, something that begins with a constant times 1 upon x squared. So this is big O, this function is big O 1 by x squared of x tends to infinity. And so I can form an absolutely convergent series starting from yeah. Okay. So if I do that and then I add these residual functions, then suddenly I'm getting an elegant modular relation. That is also clear from the fact that in this particular integral, you have alpha only in this cosine. And so if I show that this particular thing equals to this, and I replace alpha by beta, then this will be the same because alpha is 1 by beta, log 1 by beta is minus beta, and then you'll get back cosine t by 2 log alpha. So on the other side, you'll get this. Okay, so our first goal, or one of the two main theorems that we have done in this work, which with Rajat Gupta, we tried to extend this to any p real positive. So what one has to do really is to consider this capital phi sub p of x, where this phi sub 1 upon p, 1 comma p of x and phi sub 2 comma p of x, both are required. This one corresponding to the first generalization of the logarithmic derivative of gamma function, and this one corresponding to the second one. Okay, and note that the extended Euler constants of the first and the second kinds are given in here, are defined in this way. They also have this integral representation, each one of them. I'll not go into the details of, but in our work, we needed to devise a new integral representation. It's given by this. For the second one, okay. Now, if I really look at the main theorem of ours, this is how it looks. P is any positive real number. This is throughout the top. Alpha and beta are two positive numbers. We can extend this for real alpha greater than 0, real beta greater than 0. Such that their product is equal to 1. Then you have this extension for any p, previously which was known only for p tending to infinity in Ramanujan's case. So you get an infinite class of infinite families of identities from here. And now the Riemann C function integral looks like this. So here is where I would like to pause a little bit and say the difficulty in getting such a formula. When we had Ramanujan's formula here, we knew that, of course, we have to have a P everywhere. And Koshlikov had given this generalization of C of T by 2. I mean, C of T was C sub P of 2 that I had discussed before. So we initially started to put P here. You see, this is squared. Okay, and this is a real function. I could have taken this outside of this modulus. So psi of T by 2 squared. But note that this is in terms of this psi sub P of S, right? Defined in terms of that. And that is in turn defined in terms of this omega P of S, which is not a Dirichlet series. So if I have to analyze this integral through the theory of Mellin transforms, if I put C sub P of T by 2 squares, I will not be able to really get to using the theory of Mellin transforms because I don't have the Dirichlet series with me for omega sub P of S. And when I convert from here to S equal to 1/2 plus IT, where I have this thing then converted into the line integral 1/2 minus I infinity to 1/2 plus I infinity. There I will be getting, upon using the definition of C sub P of S, I will be getting omega sub P of S. And then I am not able to write it as a Dirichlet series. So how will I be able to get to this infinite series here? So that was the main trouble. We did not have an idea as to where exactly the P will go. But then we decided to resort to a completely different technique of starting with this thing and to represent it as an integral and then try to transform it into corresponding integral. And after having that written as an integral, then try to see how it would be converted into such a type with P in there. And to our surprise, we found that there is P only in one of them, not in both. Now that we have found that there is P only in one of them and not in both, one can now go with this and expand, use the theory of Mellin transforms to get another proof where one would be able to now expand at least the zeta function in here as a series, summation 1 upon n plus, and then go with the residue theorem and all. But not knowing what that, in order to discover this identity, we did not know, why is it that only P appears in one of them? Now that we know, of course, we can go and then get a second proof out of it. Okay, so as I said, P tends to infinity gives us a transformation of Ramanujan from the lost notebook. And P tends to 0 also gives something in the theory of Riemann zeta function, but a new identity. And for any other P, of course, you have infinite family of identities, infinite family of transformations. So I won't go into the details of the proof. Initially, I had thought of going over, but I don't have enough time. So I'll just very briefly say what goes into it. First of all, you show that both these series are absolutely and uniformly convergent. That can be done using simple inequalities. It's not very difficult. One has to really go through all of this, but I have only 10 minutes, in fact, 9 minutes left, so I'll skip over all these details. But one can actually show them to be absolutely and uniformly convergent. Then, once you show them to be absolutely and uniformly convergent, the idea is to convert that series into an integral, and not just that series, but the whole expression involving alpha, the whole expression involving beta as an integral. So how do we do that? We write this using Koshlikov's formula as an integral. Because of the absolute convergence and uniform convergence, we are able to interchange the order of summation and integration. Now we can use the familiar partial fraction expansion for cotangent hyperbolic, which is rephrased in this form, to write this whole thing to be a single integral. This C of T is P plus T upon P minus T. Okay, so this has dependence on P, even though you don't see it here. This is the notation that Koshlikov used and we have retained. Okay, and then note that we have a bunch of residual terms involving log and extended Euler constant. So we use this log, we write log in terms of an integral, a Frullani's integral, and then we combine them in a clever way because we need this later on. If you remember, I said to you that we needed a new representation for Euler's constant for this CP2 that we had to devise. And I don't want to go back, but if you go back in there, then there is an expression which has this thing in the front. And that needs to get cancelled. If you pair it up in this way, you take this log and have this constant in front, then you exactly have this thing in CP2 as well, which gets cancelled, and then that leads to this integral. Similarly, one can actually get the integral for another combination of CP1 and phi2, p. Also note the combinations. If it is phi2, p, it is not CP2, it is CP1. If you have phi sub 1, p on the previous slide, or here as well, it's not CP1 but the CP2. So you really need both. And so the idea is to add the two equations. If you add, the whole expression involving alpha that you have turns out to be this one. It can be written in this two form. And in the previous work of myself with Professor Brun, we showed that this integral equals 0, just 0. So you just get this one. And from there, and another generalization of a result of Ramanujan from his published paper, the theorem follows. So we have this, you replace just alpha by b, 1 by alpha or beta, and you get the whole thing. Okay, now let me, in the remaining 5 minutes, say something more. When p tends to 0, then we get this transformation, which itself is a new one. Unfortunately, I don't have time to go over the details of it. But let me come to the second part of our paper. So the famous formula of Ramanujan for odd zeta values is this. It's an almost modular relation, but not exactly modular relation because you have this as the obstruction to modularity. But alpha beta equal to pi square, and you have this. And this is actually a very important relation in the theory of modular forms because it encapsulates not only the transformation properties of Eisenstein series on SL2C, but also their Eichler integrals, the transformation properties of the Eichler integrals. Also, it has in it embedded the transformation formula for the logarithm of the Dedekind eta function. So that is also there. So Koshlyakov, see here, what is the one which forms essentially this Lambert series or Eisenstein series if I look at negative values of n? This 1 upon e to the x minus 1, this thing. Now Koshlyakov has two different generalizations of 1 upon e to the power t minus 1. It's this one and this. When p tends to 0, this reduces essentially to sine hyperbolic 1 upon sine hyperbolic t by 2. And this one becomes minus of 1 upon e to the t plus 1. Because you see, you put t equal to 0, you get minus 1. So you put minus 1 here, you get minus 1 upon e to the t plus 1. Okay. So the first question that we have had in our mind was, okay, are we able to extend this formula Ramanujan for zeta sub p of 2 n plus 1? Yes, a very symmetric and nice formula exists for zeta sub p of 2 n plus 1. It is given by this. It's in terms of the generalized Bernoulli numbers, which are given by Koshlyakov. I'll skip the proof, but I want to emphasize that a corresponding formula for eta sub p of 2 n plus 1 does not exist, or at least we haven't been able to find out. And partly the difficulty lies in the fact that it's not a Dirichlet series. But for zeta sub p of 2 n plus 1, yes, you have a complete generalization. Again, if you let p tends to infinity, you recover Ramanujan's formula. If you let p tends to 0, you get a new formula which was not known. It is a formula for a special case of the Herbig zeta function. So zeta of s comma 1/2 is when a is equal to 1/2, right? So for that, there wasn't known a Ramanujan type formula, but we found it. So it's a very nice one. And now you have many other results that you can do similarly as in the case of the Riemann zeta function. For example, you have this corresponding transformation for logarithm of the logarithmic derivative of the Dedekind eta function. That one, you have a p analog of it. And if we let p tends to infinity, we get that. This is nothing but the transformation eta of tau equal to square root of minus I tau eta of minus n by tau. So I mean something similar. I may have written the constant on the other, said the constant on the other side. But this is exactly a rephrasing of that. But p tends to 0 gives a new identity. For m less than minus 1, the sum involving the Bernoulli numbers vanishes. And so you have this beautiful modular relation. If you specialize alpha beta equal to pi, see alpha beta equal to pi square, right? If you specialize alpha beta equal to pi and m to be an even positive integer, then you have the same thing equal to minus of that thing. So this gives you this explicit representation for this series in terms of these odd zeta values of zeta sub p. And then again, you recover known results if p tends to 0. For p tends to infinity. For p tends to 0 also, this is known in this particular case. It's due to Apostel. It's in one of his books. For m equal to 1 minus 1, which is an analog of the transformation formula for E2, which is a quasi-modular form, you have this extra thing which is an obstruction to modularity. And again, you have number of special cases. These ones, this one is known, but this one is a new result. Now, let me just say, I'm almost out of time, but let me say that from this main theorem, you're also able to get a Lurch type formula. What is Lurch type formula? It's something where you put alpha equal to beta equal to pi. So you have only one zeta function and you have only one Eisenstein type series. I mean, in the base case, p tends to infinity. So we can get a corresponding result of that kind here. And then when we let p tend to 0, as I said, we always get new results. I mean, most of the times we get new results. So here are two interesting results that we got for zeta of 3 and zeta of 7. So these are not, to the best of our knowledge, these are new ones. And that comes from a more general result, which in turn is a special case of a more general result for any p. Okay, so with I'll just take maybe 2 minutes. So there, with concluding remarks, I just wanted to point out that we have merely scratched the tip of the iceberg by studying Koshlikov's theory, which lay dormant from the mathematical community, in the mathematical community, sorry, for about 60 to 70 years. It wasn't that nobody knew about it. As I said, in Kisunko's PhD thesis, he makes a very, very brief, it's just one reference that, okay, Koshlikov studied this zeta function, but there are, to the best of our knowledge, we checked everything that we could find on the internet, on MathScience, on Zentlblatt Math, and everywhere. We did not get any reference on Koshlikov's manuscript. So even the Kisunko's reference, it's not given anywhere because that wasn't published. It was a PhD thesis, but we got it, unfortunately. There are fundamental questions yet to be answered. Let's see, start with the zeros of the Koshlikov zeta functions. Koshlikov himself shows that there are non-trivial zeros at negative even integers. He also
I hate to interrupt. You'll have to bring this to an end very quickly.
Sure. Sorry. Yeah.
But,
I just wanted to.
I mean, these are fantastic formulas, but yeah, we'll have to.
Sure. Maybe in a minute, if I take a minute.
Yeah.
Okay. So there is a generalized Euler formula, and with the help of that, if we look at functional equation, then we get the corresponding formula for eta sub p at negative odd integers. But there are no formulas for negative odd integers for zeta sub p. And partly that is due to the fact that zeta sub p of eta sub p of s is not a Dirichlet series. So that is one problem. The another problem is that we were able to get Ramanujan formula. And now this is the complementary to what I said before. So zeta sub p at odd integers, we have Ramanujan type formula, but not for eta sub p of odd integers. For negative odd integers, here is where we fail to get a formula. But there is a formula for negative odd integers for eta sub p. What about non-trivial zeros? Okay, that's a big question. And then let me skip this part, but there are some inequalities that you get from combining some of the transformations that I said as p tends to infinity, p tends to 0. So there is a lot of stuff that one can actually get from even these modular relations. So with that, I'll stop. Thank you.
Thank you, Professor Dixit. Incredible collection of formulas. Very beautiful. Are there any questions? Do people have questions, please? Well, look, if there aren't any questions, I think we're going to have to break for lunch. Again, thank you, Professor Dixit. And we'll pick this up, I think, 2 o'clock Indian Standard Time, okay?
Sure.
Thank you. Okay.
Thank you.
Well, for now,
Yeah.
I